Hey, there we go. Just playing with settings and testing stuff. Hi, everybody. Welcome to the extra lecture. I don't like having these because it means that I have a 6-hour workday most of the time. But even worse than me having to work more and you having to listen to me more is us not getting through the material, and that would be really bad. Yeah, I guess it is noon, isn't it? It's afternoon now. Crap. Well, my day just started, so like most Mondays, I didn't get much sleep because Monday is my acclimating period. So hopefully I don't say anything too stupid. And by stupid, I mostly just mean wrong. Like, I'll just say the wrong thing because I'm thinking of the topic or whatever. But um, we should be okay because we're in the back half of chapter 3. And I don't really actually mean half. I mean, we're like almost done. We might finish this today, and that's my goal, but there are a lot of slides, and we'll just do the best that we can. So we might get all of them done, but in any case, we'll finish tomorrow if we don't finish today. I thought I went back and looked at the video from last week, and this is where we ended. But now that I'm still in that brain fog because I've only been awake for an hour and a half. I believe that the last thing that we did, let me put it on the screen, was we definitely did this. And then I talked about how there were some exceptions, but we had already covered the exceptions. So just a reminder that the first time you pair electrons when looking at ionization energy, this electron-electron repulsion slightly lowers the ionization energy for the element that you're looking at. So when you go from group 5 to group 6, and let's actually write that there. Not group 5, but group 15. You're always adding an extra electron into an orbital that already has one. So the ionization energy of group 16 is always going to be slightly lower than you would expect it to be due to that electron-electron repulsion. I think in nearly all cases, it ends up being lower than the ionization energy of group 15. However, there might be some weird edge case where they're like equivalent or they're just really close or whatever. But this electron-electron repulsion helps push the electron away. And then you see the same thing when you go from 2p to 2s. So when you go from group 2 to group 3, group 13, you're going from the s orbital to p orbital. P is always higher in energy than s, so the ionization energy always is a much lower for group 13 than you would expect it to be. All right. And hopefully we remember our discussion of ionization energy for Monday. We're going to talk about ionization energies for the second electron and beyond today, because we've talked about ionization energy 1. For IE2 and 3 and 4 and 5 and so on, there aren't as many predictions that you can make, but there are still some, and there are some that can actually let you determine what an element is. And we're going to look at that today because in the lab that I'm assigning this week, you're going to see a little bit of this in the photon emission spectrum lab, which I have to actually make a video for because that needs its own video. And we might not have time to go over it during the lecture. So I'm going to try and prepare that tomorrow night or at some point, and then I'll upload it to YouTube. Like, I'm actually going to record it on my PC as opposed to streaming it, and then, like, edit it and put stuff in it. If you took 140 with me, it'll be kind of like the lab video, minus the cheesy music, because I'll be talking over it the entire time. So that'll be coming up this week, but it does have to do with ionization energies first and then beyond. So let's talk a little bit about that. What does it mean to ionize 2 or 3 or 4 electrons in terms of like the structure of this system? Well, every time you pull an electron away from something, we'll draw a little picture here. So here's my electrons. And let's suppose that I ionize one away. The remaining electrons are then pulled in more tightly because the force that is acting on them. I guess I should be pointing my arrows this way, huh? The force that is remaining is now spread over fewer electrons. And if I remove this electron, then it's even more still for the remaining ones. And this increases and increases and increases. So we could just do something like this. And you could just do this as long as you have electrons. So the first ionization energy is whatever it is. Then the second one is more than that. And the third one is more than that. And this is universally true. There are no weird trends in terms of, oh, something is slightly less than we would think. No, it's always just higher and higher and higher and higher. Now, you can actually make some sort of prediction as to how much higher it will be to some extent, because if I have 4 protons and 4 electrons and I pull off the first one, now I have 4 protons pulling on 3 electrons, so it's going to be like 4/3 as strong. And then the next one will be twice as strong because there's 4 protons pulling over 2 electrons. Now, that's only a first order approximation, because as you do this, the distance is also decreasing. And so you have to factor in distance too. So this will only kind of get you in the ballpark because we're not accounting for distance in this estimation. But it's a good idea to see, like, oh, okay, it's roughly doubling X number of times or whatever. Now, in some cases, the amount of energy that is required increases by far, far, far more than we would expect. And I call this a huge jump. And I call this a huge jump with an H in it and not a huge, because I'm an educated individual. But what do I mean by huge here? What I mean by huge is by a large factor of like 5 to 10 times or more. It should be pretty obvious when you look at the data. So we'll write that in there. What that means is I'm going to give you data, and you'll get to look at it, and you'll notice, oh, there's the huge jump. It went up by like a factor of 10 or a factor of 8. Now, why does that happen? That happens if you try and ionize a core electron. So what's physically happening here is when n decreases, because you strip away all of the electrons in the valence shell, the valence layer becomes the next layer down, and so n decreases. And because of that, the electrons are closer to the nucleus. Now, if you remember your Coulomb's law, decreasing R causes the energy to increase. And decreasing R can very quickly do this because the numbers for R aren't very big to begin with, right? And so when you remove the first valence shell, it's not uncommon to see the distance change by like a factor of a half. Like it gets half, the electrons are now half as far away, or even more than that. Just because of all the protons pulling those electrons in towards the nucleus. All right, so that's the theory behind it. Let's actually look at the data here. So this is sodium right here on the left. And you can see that the first ionization energy right here Takes 496 kilojoules per mole to ionize. What that means is that if I have a mole of sodium, oops, I lost a 6 in there. There we go. And a K. If we had 1 mole of sodium, and I put in this much energy, I would remove a mole of electrons, and they would all be the 3s1 electron on sodium. So that's what these numbers mean. These are all in kilojoules per mole. Obviously, it's not very hard to remove 1 electron in terms of energy. Like, if you flicked something with your finger, that's far more energy than an electron could withstand. But working with those teeny tiny numbers on the order of like 10 to the minus 19 is not super useful to us. So we represent energy for ionization in kilojoules per mole. Now you'll notice that to go from IE1 to IE2, we went up by a huge jump. It was almost a factor of 10. And so what happened here was... So I have to hit clear, unfortunately. If I write out the entire electron configuration here, here's my IE1. But if I go to the next ionization energy, this would be my IE2. And you can see that it's coming out of a core shell. When you're pulling electrons out of the core shell, the energy to do that is much, 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 much higher. You can see the same thing for magnesium on the right here. So here's magnesium, and if I write its electron configuration, and then I start ionizing it, well, I can get the first 2 out. And that's relatively straightforward. But if I take the third one out, it's going to take way more energy because I'm removing a core electron. There's my huge jump from this to this. And so when you look at the numbers, it should be pretty obvious that you have a large jump in energy. In fact, what you can do usually in most cases is just look to find the biggest jump in energy. And that'll be where you start to ionize core electrons. Now, if you didn't have the identities of the atoms here, how would you be able to solve this problem? Because you're going to see a problem like this on the practice slide in just a second. So if I go like this, and I ask you, what period 3 element is this? Then what you would have to do is you would have to say, okay, well, I know that the big jump means core electrons, so all the small jumps are the number of valence electrons. Because here's 1 valence electron, and then the next one must be core. So I only had 1 valence electron. And if it's in period 3, that must be sodium. Here I have 2 valence electrons. And because the third one is the core, I must have these 2 valence electrons, so this must be magnesium. Now, can you tell the period? Not without other data, unfortunately. Like, I would have to give you data for each period so that you could compare them. And you would see that the ionization energies actually go slightly down as you increase the period number. And that's because electrons are getting further and further away. But it's not as reliable because electrons tend to get really far away early on. So like n equals 2 is way further away than n equals 1, as opposed to n equals 5 and n equals 4, which are more or less right next to each other. So that's not as reliable. But this group determination is actually very reliable. All right, so I'm going to give you this practice problem, and then I'm going to give you this set on the second page. So we'll start here. What I want you to do, for each set of 4 atoms, and this is sort of a review of last week too, I want you to rank the following atoms in order of increasing first ionization energy. Now at the bottom I have elements with the same number of protons, and then just changing their charge to make them ions. How do different ions compare in terms of ionization energy? Count up all their electrons relative to protons and rank them that way. Okay? Now, on your periodic table, you should always have a way to determine the ionization energy ranking for the elements that I give you. Now, I don't think I've given you 4 before. On Canvas, I think I'm going to give you 4 or 5 or something like that. But I have arranged them in such a way that you should be able to pick them based on where they are. So you're going to have to hunt for elements on the periodic table. And you might notice that some of them are not going to be in a line. Like you might have this weird kind of like S curve or Tetris piece or whatever. And you could still solve it. And your hint here is to write out this, make a little table for everything, and then try and justify what you have written down in your table to arrange it. We'll go over the answers in about 5 minutes. All right, I'll see you in a bit. One more minute, we'll go over the answers. All right, so let's go over these. First, let me clear that, and then let me do this. Well, that doesn't really help anyone, does it? All right, that's good now. Zoom. All right, so for all of these, remember that we like to make the little N and Z effective chart here. So I'll go calcium, krypton, arsenic, potassium. I have my periodic table here too. So let's see here. You'll notice that they're all in period 4. So this is all the same. So this is kind of a wash. Like, we don't care about this one. We just do that to it. But Z effective, if we calculate Z effectives, we're going to get this. So 2 plus, 8 plus, 5 plus, and 1 plus. And this order does matter. So remember that we can say as Z effective increases, ionization energy increases too. Because you have a stronger charge pulling your electrons towards the nucleus. It's the same reason that radius decreases, because the electrons are being pulled closer and closer and closer. So what we'll do is, since they're all only differing by Z effective, we'll just sort them by Z effective. So the ionization energy for potassium must be the least. And then calcium. Oops, that doesn't really look like the symbol for calcium there. And then what's the next one? Arsenic. And then krypton. These are all IE1, by the way. So there you go. There's the first order. Oh, I now see the issue. I actually overlooked something in some of your answers there, Elon. Make sure that you're doing them in increasing order. I think, like, the first one there, I think, was in reverse. The second one looks good, though, and we'll show why in a second here. So let's just go down here. So now we've got sodium, cesium, rubidium, and potassium. And for these, I'm going to do the something something obvious thing first. They're all in the same column, so we don't care about Z effective, so whatever, right? But if I look at their period number, so sodium is in period 3, and then potassium, rubidium, cesium. So these differ, so we'll care about those, because as N increases, Z effective, not Z effective, sorry, ionization energy decreases. And that's because the electrons are farther away from the nucleus, so they're easier to pluck off. Whoop. There's less attraction to the nucleus due to distance. So I just arrange them in terms of distance. The furthest one away is the lowest. And there you go. That should be the order for that set. All right. And then the last set here. This is the most similar to what you'll see on the quiz because I've given you a set where they're sort of scrambled. So if I look at elements in what periods they're in, so chlorine and argon in period 3, bromine and selenium are in period 4, so we have differences there. And then when I do Z effective, I get this. And you're probably thinking, how the heck am I supposed to manage this? And so here's the strategy that I would use to solve this problem. So first of all, remember that N increasing I keep writing Z effective. There we go. Means that the ionization energy is lower. And if Z effective is lower, then I will have a lower ionization energy as well. So of these, you can choose the one that should have the lowest ionization energy because it has the highest N and the lowest Z effective. So selenium has to be the lowest. So we got that one done. Now you can do the opposite of this. You could figure out which one has the highest ionization energy by finding the one that has the smallest N and the largest Z effective. So if I do this, this gets bigger. And if I do this, this gets bigger too. Okay, what's the other end of the equation? Which one has the lowest N and the highest Z effective? Well, that's this one. So we can add that to our list too. That's got to be the highest of this set. And now what we have to do is just do comparisons between the two. So I know that if I compare selenium and bromine, this is higher than this one. So bromine's going to have a higher ionization energy than selenium. And if I compare chlorine and argon here, chlorine's going to have a lower energy than argon. So I know that these are true. There we go. I'm going to put them in blue for now. I'm going to put a big line here just to say that we haven't figured out this relationship yet. So we know that these two statements are true. And then finally, we have to compare bromine and chlorine. And you can see, oh, well, they have the same Z effective, but bromine has a higher N, so bromine must be lower than chlorine. And then once you know that, you have the entire order. So you can deduce each one in pairs, and then there's only one way you can arrange them, because this relationship is true, this relationship is true, and this relationship is true. Therefore, I must arrange them in this order. I can't swap any two without breaking a rule somewhere. So there's not going to be some weird exception where it's like, oh, this is lower than bromine is lower than chlorine, but it's also lower than selenium. So the Z effective piece is the charge that the electrons feel. And even though there are more valence electrons, the ionization energy still goes up. Like you might think, oh, there's more electrons. Why is my energy going up? The electrons should repel each other. But it turns out as Z effective increases, even though there are more electrons, the protons win overall. And so they pull harder on those electrons. And the reason for this is because when you're adding valence electrons, they go roughly at the same distance away. Because you're putting them all in the same orbitals. So I'm putting them all on p orbitals. And as a result, their distance isn't that much farther away from the nucleus. But the force that's pulling on them is much higher. So as Z effective increases, ionization energy goes up too. It's the same reason that radius decreases as Z effective increases. Okay, I gotta clear this, unfortunately, because we're out of space on the canvas here. Alright, so let's rank the following in order of increasing ionization energy. Now, if I do this sort of analysis for these ions, then what I see is that I get the same N every time. But Z effective does change slightly. Well, actually, in this case, it doesn't. So, because I have not removed a core electron. So, these all have the same Z effective pulling on them. So, what we can then do is we can look at the next thing, which is number of electrons in the valence shell. And we actually see a difference here. And so what we can say is that we have this charge and it's going to pull on this many electrons. Since we're comparing with the same charge, we can say, oh, well, an effective charge of 4 protons is going to pull 4 electrons to some distance away. But it's going to pull 5 electrons less effectively. So these electrons must be further away than these electrons. And as a result, the ionization energy for the case with 5 electrons will be lower than that for the case with 4 electrons. Because it's easier for us to take away an electron when the electrons are further away. We'll actually write that down. Now in this case, there are this many effective protons pulling on 3 electrons. So these are going to be closer to the nucleus. So it's going to be harder for us to remove that electron. And so there's the ranking for that one. Now, in other words, what you can say is the thing with the most valence electrons is easiest to ionize. The thing with the least valence electrons is the hardest to ionize. And so, by that token, we should also observe that this is the case too. And that makes sense because of what we just said. Removing extra electrons is harder and harder and harder and higher. What we're actually looking at is, instead of saying that these are the first ionization energies, we could say that this is the first ionization energy. Or actually, this would be the second of sodium. This would be the third of sodium. And this would be the fourth of sodium. Because to remove a second electron from sodium would be like removing the first electron from sodium plus, and so on. Just another way to look at it. All right, I'm going to give you this table now. Now, the top question is going to take you all the way back to the very first day of class. I dropped cesium metal in water. I didn't do it, but an instructor did on YouTube, and I showed it to you. And we saw that cesium detonated in like 3 frames. Like, it was super fast. But sodium was much, much, much more slow. And what I want you to do is tell me, why did we observe those effects based on quantum mechanics? And the hint I have for you is that in order for the reaction to occur, we have to do this. So our metal has to do this for this reaction to occur. So why might cesium be more explosive than sodium, based on your observations and what you know about quantum mechanics now? So type your response in the chat when you think you got it. And then down here on this table, here's my table of data. And so these are all in kilojoules per mole, and I got these from Web Elements because all these numbers are available online. I want you to tell me what the mystery element is. If the mystery element is in period 3, that's important. If I don't tell you what period it is, you can't solve it. So go ahead and try these problems. I'm going to type my response to your question there, Greg, so that I can be quiet while you guys work. My alarm is going off, which is saying, hey, you need to get ready for class. Except I'm already here. All right, one more minute. We'll go over the answers. All right, so the first question here, why is cesium more explosive than sodium metal? So we're sort of dancing around the answer in the chat here, if you're reading the chat. Let's show why this is in a picture. Oops, I didn't quite capture the top there. And so the hint I gave you was that these elements have to become cations. What I'm going to write on the screen here I'm going to write the equation for what actually happens in the water. You don't actually need to know this, but just in case you were curious. And I have to balance the equation here, so hold on. Here you go. There's the reaction. You can replace cesium with sodium, and it's exactly the same thing. But what's happening here is this is cesium metal, but this is cesium cation. So we're actually ionizing cesium in this process when you drop it in the water. You rip off the electrons and you pass them to hydrogen, which is why you make hydrogen gas at the end there. Your H pluses in that are ripped off of water become H2. Now, if that's like, well, what the hell is that supposed to be? We're going to talk about these types of reactions in 163. These are called redox reactions. And all alkali metals do this. You drop them in the water and they form bases. And we'll also talk about acid-base chemistry in 163 as well. But if I draw my diagram here, I think cesium goes down to 6, right? Okay. And then we'll put n equals infinity right here. Here's where my electrons for sodium are. Here's its valence electron. But cesium's is way up here. Now, in order for the reaction to occur, I have to get this electron to be ionized. Ionization is just moving an electron up to n equals infinity. If I do that, I have to pay this much energy. Now, when I make the products, I produce energy. So I get the energy back, which is then used to start a new cycle of the reaction. And any excess energy is what we observe. We would observe like the flame, the fizzing, the hydrogen gas being burned, etc. Now with cesium, you don't have to move it as far. Oops, hold on. Let me be consistent here. I only have to put this much energy in, which means that if I'm getting the same result out from like making hydrogen and making hydroxide and whatever, I'm not investing as much energy to do this. And so this extra energy can be used for more ionization. In other words, if I'm getting this much energy back overall, I'm getting way more with cesium, and you see that as a faster reaction. So if more energy is available, more ions get ionized, or more atoms get ionized more quickly. And so this is a sort of just like intro to thermodynamics, which is what you're going to study in 162, which, by the way, is just around the corner because we're almost done with this class, believe it or not. So that's the answer to that first question, is that, hey, I use less energy, I get to keep more of the energy that I produced to make the reaction go faster and faster and faster with cesium. With sodium, I spend more of the energy, so I don't get as fast as of a reaction. All right. I don't actually need this screen for the second one, so we'll just leave that on the screen. You can pause it if you want to keep looking at it. But if I go back here, remember that if you can find the huge jump, you can find the number of valence electrons. So right here is the huge jump, and there is one valence electron in sodium. Down here for silicon, you don't really see a huge jump. It would actually be over here, but I found that if I put the fifth ionization energy, my table got too long, and the numbers got too, like, compacted, so I only put 4 in here. But looking at the mystery element, you should be able to tell that this is the huge jump. And so there must be 1, 2, 3 valence electrons. What element is in period 3 and also has 3 valence electrons? Well, that's aluminum. So the mystery element based on this data must be aluminum. There you go. I think that that's everything we care about for ionization energy. Yeah, we're going to do electron affinity next. So when we come back from the break, we're going to take all of the information that we learned from ionization energy and then apply it to this new topic called electron affinity. Electron affinity is just the opposite of ionization. Electron affinity is dropping electrons into atoms. How much energy do you gain? Well, if removing an electron causes you to pay energy, it has a positive energy associated with it. Electron affinity must have a negative energy, and that's the amount of energy that your atom gains when you drop an electron into it. And you're going to find that there are some surprising numbers that are involved when we look at that. So let's go to the break. Let me put the timer on the screen here. I got to reset the timer. Hold on. Oops. I was using it for a different thing this weekend, so... Oops, there we go. And we'll get started, and we'll put on the Metroid music. So I'll see you in just a little bit for that, or after the break. Alright, we're back. Alright. During the break, I did a little bit of setup for the next section, which is electron affinity. So what electron affinity is, like we said before the break, electron affinity is the energy difference that occurs when you add electrons to atoms. So instead of ionization being taking electrons away, electron affinity is we're putting electrons in. And just like ionization energy, you can have multiple electron affinities. So EA1 would be the first one, EA2 would be the second one, and so on and so forth. We're really only going to deal with EA1 for this class. Some weird things happen when you go past one extra electron in many, many cases. Generally, that is, the electrons repel, and EA2 is a giant positive number. But not always. And it very much depends on the atom and the electron configuration and what you're looking at. So we're going to try and look at some trends here. For example, chlorine loves electrons, which we're going to find out in Unit 4 when we make ions out of things. We find out, chlorine always becomes Cl-, fluorine always becomes F-, so on and so forth. And so dropping an electron into chlorine produces a lot of energy. Now, if you were wondering where does the energy come from in the previous reaction where you're talking about sodium or cesium exploding, and us having to add energy into the system to remove the electron, this is where the energy comes from. When you drop energy into atoms by dropping electrons into them, sorry, let me rephrase that. When you drop electrons into other atoms, you tend to refund that energy because the electron drops from n equals infinity to whatever open orbital is available. And if it falls farther, then the amount of energy you had to put in to remove the electron from the other atom, you get a net amount of energy back, and the excess energy can be absorbed by other atoms to remove their electrons and sustain the reaction. So let's go over here to this screen. So what I've done during the break, I copy and pasted the table of electron affinity from your textbook. So this is OpenStax. This is figure 3.35. It's in section 3.5, which is what we're doing right now. And we don't really have electron affinity data for transition metal, so we're just going to ignore it. But what we're going to try and do is we're going to try and look at trends that we can see on here. And in order to do that, I need more space, so I'm going to zoom this out a bit. So let's look at the obvious ones first. So as I go down the periodic table, oops, I don't want to use the word decreases here because we're working with negative numbers. So I'm going to write it like this. The electron affinity becomes a smaller magnitude number as n increases. Now, electron affinity should be negative because we're dropping electrons in. So if I go down here and I draw a diagram for this, and here's the nucleus. If I put n equals infinity up here, remember that there should be some energy associated with this. And that as I go down in energy, my energy becomes more negative. So I'm going to just put some arbitrary n values here. I'll just call that 1, whatever. If I drop my electron and it lands in n equals 6, I'm only going to get this much energy out of it. So this will be a small negative number. But if I drop an electron and it goes further, then I get way more energy back. So we'll call it value. So as n increases, we're noticing that the amount of energy that we get back goes down. And you could see that in all of these trends here, is that you get more energy if the electron falls further. So dropping it into H gives you more energy back than dropping it into cesium. Now, this is not universally true, of course, because that would be too easy. And you can notice that a lot of these numbers have weird exceptions here. And there are various reasons for that. For example, n equals 2 is very small, so a lot of the n equals 2 numbers, which you can see over here, tend to be a little bit less negative than you'd expect them to be. And then the trend tends to resume. However, it is obviously not perfect. Really, the ones that we care about are this column and the first column. They tend to follow the trend the best. All right. What else can we observe here? Let's get a new color here so we can do this. As we go across the periodic table from left to right, Z effective increases. As Z effective increases, the electron affinity tends to increase. But there are some weird things that you notice, and you've just noticed it right now. Why is n 0? That is what we call a coincidence or a fluke, it turns out. But there are some specific columns that have weird things going on, and those columns are these. So 2, 15, and 18. And I'm going to write weird. Really, what I should write is exceptions, but we can actually easily explain these. And so let's do that real quick. I wish I had drawn this on another layer, because now I have to erase it but redraw it. All right. So let's try and explain what happens in group 2. If I draw the electron configuration diagram for a group 2 element, so for example, I gotta write P in there. All right, so let's look at, say, beryllium. Here's what beryllium looks like. And now I'm going to add an extra electron in there. That's going to go in here. What ends up happening here is that for the second element, the electron affinity should be a little bit less intense because there is an energy difference between S and P. But it also turns out that this electron in the 2p orbital is just too far away. For an atom with Z effective of 2+, it can't hold onto an electron in the p orbital. The p orbital is too high in energy relative to the s orbital, which means that electron is too far away. You can think of it as effectively like if I was considering that these electrons were my valence electrons, as shown there. Even though the 2p electron we're adding should also be a valence electron, that energy difference is enough for the electron to think, oh, there are 4 electrons already there. I'm getting shielded out. And so, because the attraction to the nucleus is so small, the electron doesn't stick. It just flies away. It bounces off. Now, if you hold the electron in place by giving it energy, which is what is going on here, if you put in energy, you can put your hand in the way and hold the electron from flying away, and it requires 240 kilojoules per mole to hold the electron in there. So, the reason that the group 2 elements do not have a negative electron affinity is because the 2p orbital, or the p orbital, I should say, is higher in energy than the s orbital, and z effective of 2 is not sufficient to hold on to it. So let's write that down. Okay, cool. Let's do the next one. There we go. Okay, so let's look at group 15 now. So we'll look at nitrogen. Nitrogen looks like this. 1, 2, 3, 4, 5, 6, 7. Where does the extra electron we're adding in go? Well, it has to go in one of these orbitals that is paired. Now, oxygen can do this just fine. It pairs an electron, but it has a Z effective of 6+. With a Z effective of 5+, the electrons just repel each other because we're pairing them in the same orbital. So the electron-electron repulsion from pairing our electrons reduces the magnitude of the first electron affinity for elements in group 15. And interestingly, the result for nitrogen is that it just ends up landing on 0. So the first electron doesn't stick to nitrogen effectively at all. And that's just sort of a fluke. It just happens to have landed real close to 0. It's not exactly 0, because that's 1 sig fig. But it's real darn close, and it is a positive number. But you can see all of the other elements in group 15 here. Their numbers tend to be a lot less negative than their neighbors. And the reason for this is the first time we have to pair an electron when doing EA. And the Z effective for that atom is not prepared to accommodate that. As you add even one more proton, you can see that oxygen is happy to accept an electron. Sulfur is happy to accept an electron, and so on and so forth. Then the last one is group 18. And we can use the same diagram for this. I just need to erase this guy right here. So if I'm looking at neon, where does the next electron go? Well, it's got to go through here, right? Now, this is a totally new valence shell. So 3s is objectively much further away than this. And these electrons would feel Z effective 8, but this electron feels this. And if there's no positive charge pulling on it, then why is the electron going to stay? It has no business here. And so, oops, holding the eraser down there. For noble gases, when you try and add an electron to them, the noble gas doesn't want it. The end result is that the electron doesn't stick because you're adding the electron to a new valence layer, and Z effective at that layer is effectively 0. Because the number of protons and electrons between that electron and the nucleus cancel out. So that's electron affinity. Electron affinity is weird, and it's not great at following trends. For example, neon ignores this to some degree, but the rest of them don't. I have no idea why neon is negative. Just what we experimentally observe. But there are some trends that we can predict, and so I will give you elements that fall in these trends. I would ask you to use the trends and not refer to this number and simply type in the order, because there's no reason to look up this chart. Just follow the trends that we have over here, and then note what the exceptions are. And then that's electron affinity. All right, so the takeaway messages from this are that electron affinity is when you add an electron to an atom, it is almost always negative. And then the trends that we observed on the PowerPoint slide. And so that's what I'm talking about here. And then those are just more exceptions that we just discussed. All right, so I'm going to give you a bunch of pairs here, and I'm going to ask you to predict which element has the more negative electron affinity. Okay? Now, use the trends that we talked about. Don't just go, oh, I'm going to just scroll back 10 seconds in the video and go look at the chart and then compare the numbers. Don't actually do that, because we're going to see that the numbers don't actually always match up. But you should be able to make a prediction here. For example, this first one, they're in the same period, so which one has a higher Z effective? Well, this one is Z effective 3 plus and 4 plus. Electrons are more attracted to the nucleus when there's more charge pulling them in, so this must have the higher electron affinity, more negative. Do that for the rest of the pairs, and we'll go over the answers in a second. One more minute, we'll go over the answers. All right, so when I ask you a question like this, which has the more negative electron affinity, one of the best things that you can do is you could just cross out all the exceptions, because the exceptions will always have a more positive number, right? So look for anything in groups 2, 15, or 18 are the exceptions. And just do this. Haha, you're group 18, you can't be the answer. Haha, you're group 15. Haha, you're group 2. So that automatically tells us these. Now we'll go back and do the quantum mechanics explanations in just a second, but let's do the last one that's left here. So for the sodium and potassium one, we could still do this little table like we've been doing before. And we can see, oh, they're the same Z effective. It's not going to affect it. But for n equals 3 and n equals 4, my electron falls further. For n equals 3, and therefore it will be more negative. So this must be the answer. And if you go look at the chart, we can see that sodium indeed does have a more negative electron affinity than potassium does. It's not much, but it is more negative. All right. How do we explain the other ones here? Well, all of the rest of them follow the normal trends, but the exceptions here, so krypton is a noble gas. And it's going to add an electron to a new valence layer. Let's get rid of some of this stuff here, so I have more space. For phosphorus here, my electrons pair in the p orbital for the first time. And Z effective of 5 is not enough to hold on to that as effectively. So the electron repulsion takes over and reduces our electron affinity to be less negative. And then here for magnesium for group 2, the added electron goes into a p orbital. And Z effective of 2 is not enough to hold onto the electron there. All right, that's electron affinity. Obviously, on Canvas, I can't ask you to explain your choices, like maybe through a multiple choice question or something like that. But if you're asked, like, pick the element that has the more negative electron affinity, remember to follow the trends, N and Z effective. The further down the electron falls, the more negative the electron affinity will be. And if Z effective is higher, the more electron affinity will be, the more negative it will be. And then just cross out any exceptions. They're not going to be the answer for most negative electron affinity. All right. I believe that that is the end of quantum mechanics. Hooray. No more quantum mechanics stuff. The rest of this is just like information. This is sort of a segue into Unit 4 because we're finally done with all of the hard stuff in Chapter 3, and maybe even the class. Like, the rest is significantly easier in terms of things that we're going to do. However, it's still important to know the Chapter 3 stuff because we're going to come back to it, to refer to it. All right, so this next section is just a collection of trends on the periodic table that don't follow quantum mechanics or follow more advanced stuff that is beyond the scope of this class. So, this is Dmitry Mendeleev. Dmitry Mendeleev observed all of these trends with elements long, long ago. And what he did was in 1869, he took all of his observations and put them together into the form of what he called the periodic table. Now, his periodic table looked different back then, and we can actually find a copy of that. Let me go look one up real quick. So his periodic table looked like this. Let's window capture that. So we only really need this, and I just want to blow it up a bit so you can see it. There we go. So you could see his periodic table looks a little shorter than ours. But what he was doing was he was compressing it into columns based on trends that he observed. And these would be things like, oh, all of the elements that are in group 1 are reactive with water. All the elements in group 7 are reactive with metal. All the elements in group 2 are slightly reactive, and so on and so forth. And that's interesting and cool and all. But the most important thing about this is that anything that is in red on the screen was not an element that was known to Mendeleev at the time. And so he had a periodic table with a bunch of holes in it. For example, gallium and germanium, those are in red. And those had not been observed or like isolated or documented yet. And so Mendeleev was able to predict, I bet there are elements that exist here, because why wouldn't there be? So I want you to look for an element that has these properties. It should be similar to silicon and zirconium. I'm thinking of germanium now. Let me go back to gallium here. It should be similar to aluminum and indium. Should have a similar formula when reacted with a chloride. It should have a density roughly between these two, so on and so forth. And it turns out that he was able to predict that those elements existed and give people a way to actually look and find them. And he was right on the money just based on how powerful this predictive tool is. And we've been using the periodic table to predict stuff all throughout Chapter 3. So its structure is set up in such a way that it conforms to electron configuration, which gives us a very powerful tool for use. And so there's just the whole periodic table. I'm sure that you have your own version on P-table that you're using. We're going to formally define the terms here. So groups are the columns on the periodic table. This is the scheme that I have been trying to use, is the new numbering scheme. You could see that the Mendeleev scheme sort of persists. This is the old notation where we call them A and B based on what Mendeleev numbered them as. So those are groups. Groups are columns on the periodic table. Rows are called periods, and the principal version, or the principal use of the period number is to tell you what the valence shell principal quantum number is. I'm sure that you have heard me use and refer to these terms throughout the quarter, and if you were just confused by it, those are the formal definitions. I actually have no idea why this part comes up so late in the text. I would have started with this text, but there you go. On the screen here, you can see the different terms that we use for elements. The most important on here is this right here. Oops. Where it says main group elements. The main group elements are all the elements that are in group A, according to the Mendeleev scheme. But for our purposes, they're groups 1 and 2, and then 13 through 18. We're going to be working exclusively with main group elements in Chapter 4, when we do structures and stuff like that. And those elements have their own names in terms of their group. So the first group that we care about is the alkali metals. Alkali metals are called alkali metals because they are alkaline. When dropped in water, they make a base. Alkaline earth metals also do the same thing. Skipping over to the other side, the other two important ones are the noble gases. Like all nobility, noble gases sit on their asses and do nothing. And then the halogens, because halogens are common and reactive. What's in halogen bulbs? A halogen. It's probably chlorine. These other two, chalcogens and pnictogens, I honest to Thor did not know that pnictogens was even a word until I started teaching out of this textbook, because nobody uses it. In my undergraduate laboratory, people worked with chalcogens a lot. They did oxygen and sulfur chemistry on lanthanides and actinides. So I heard the word chalcogens, but again, that's the only time I've ever heard it used. So I would not expect you to need to know chalcogen or pnictogen. Like, nobody cares. Transition metals are common enough that it's good to know what that term refers to. And then lanthanides and actinides, these are just curiosities. You may hear these called the rare earth metals. And that term is starting to fade out of use because there's nothing rare about a lot of these. In fact, they're more common than some of the transition metals. Like gold and platinum are not very common, but thorium and uranium are, as we were talking about earlier. I'm going to leave this exercise for you to do because it's just counting a period in group and then giving a label to it. So you can look up that iodine is in column 17, row 5 or whatever, and that's not really worth spending 5 minutes on. So I'll leave that as an exercise for you to do on your own time. The last little bit of this section talks about metals and nonmetals. Gold and platinum, we don't call rare earth metals, we just call them rare. A trend on the periodic table that we haven't really talked much about, but it'll be important when we get to Unit 4, is the difference between something that's a metal and something that's a nonmetal. A metal is defined as anything that has the following properties, and it has to have all of these properties to it, including Bender here. He is a metal. Metals have all of these things in common. So they have high thermal and electric conductivity. So what that means is that if you heat them, it's easy to increase their temperature and also spread that heat among any connected part of the metal. So for instance, if you have a cast iron pan and you put it on the skillet, the handle does get hot because the whole thing is made of iron. The heat will conduct throughout the entire skillet all the way to the handle, and you need to use a oven mitt or pan holder or whatever, hot mitt thing, to avoid burning yourself. Metals are also electrically conductive. That means that if you transmit a current through a metal with an electrode, It doesn't matter where you attach the other electrode, the current will transfer through it. So if you had a wire or a sheet or even your cast iron pan, you could conduct electricity with it. The current would just go straight through very easily because it's metal. Metals are malleable and ductile. Malleable means that you can hammer it into a sheet. If you hit it, it doesn't shatter or break or crack, it just tends to deform. So the way that aluminum foil is made is you just take a giant block of aluminum and you just press it until it's the desired thickness, and then you just stretch it from there. You can also just cut it and then stretch it that way, but it depends on how many moving parts your aluminum factory wants or needs to have. Ductile means that you can pull on it in one dimension and eventually you'll get a wire. The more that you pull on it, the thinner the gauge becomes. And so you could just keep doing that until you get the desired gauge for your wire. The last property of metals is that they're shiny. This is called luster. Luster is the effect of mobile electrons over the surface of a metal. This is due to how metallic bonding works, which we don't talk about in this class. I don't think that you'll actually see it in chem. Might talk about it in material science, but when you look at bonding in metals, there is a valence band where all the electrons can kind of just move from one neighbor to another. They just kind of zoom about. So that on average, there are X number of electrons near whatever nucleus. But the electrons don't stay associated with one atom easily. This is why metals are conductive. The electrons can just go wherever they want to. A consequence of that is when you look at the metal, any light that bounces or that hits the surface gets reflected in random directions by these electrons, because they bounce up to a higher level and then fall back down, emitting the same light back to you. And the end result is it looks shiny. And in some cases, if the surface is regular enough, you get a mirror. So silver is really good at making mirrors. Other metals are good too. Every metal can potentially make a mirror. But if you made a mirror out of, say, copper, like, you wouldn't see the image reflected off of it because there is a color associated with copper. Any substance that has none of these properties is considered a nonmetal. So on the screen there, I have iodine. Iodine is a nonmetal. If you hit it with your hammer, it will shatter into a million pieces. We're going to talk about more why that happens in Chapter 4. And any elements that are in between these extremes are called metalloids. Metalloids have some of these properties, but not all. They're kind of like the Goldilocks in terms of conductivity or malleability or etc. So silicon, for example, does not conduct electricity too well. It does not conduct electricity poorly. It's sort of just right. And so we use silicon for computer chips because we want to be able to control the flow of electrons through logic gates. We don't want them to flow unimpeded because otherwise we wouldn't be able to make a computer out of it. Or we could, and then the computer would heat to like 600 degrees Celsius and melt, and we would need a ton of fans for that. We already need enough fans for our computers. So metalloids have some of these properties. You can tell what an element is based on its position on the periodic table. Metals tend to be on the left. Non-metals tend to be on the right. Hydrogen is kind of the weird exception. Hydrogen is considered both a metal and a non-metal depending on what table you're looking at. And then the metalloids all follow along this little staircase here. So I'm going to just take a pen. We're going to draw the staircase. And so that line right there, this is the metal, non-metal staircase. And if you are on the left of this, you are a metal. If you are on the right of this, you are a non-metal. And if you touch the staircase, you're a metalloid, with one exception that we care about, and that's aluminum. Down here, these are radioactive. We're never going to work with polonium and astatine, so it's not worth remembering them. But every other element that touches the metal-nonmetal staircase on an edge, except for aluminum, is a metalloid. Aluminum is considered a metal. It has all the properties of metals. All right. You can observe metallic character by just going across the periodic table. As you move from right to left, things become more metallic. You can see that on the screen here. This is period 3. I chose just 4 things that I had pictures of. So chlorine on the far right is a gas. Not super exciting, not super metallic because it's a gas. Got to be solid to be a metal. Phosphorus is a non-metal. It already looks more metallic just by virtue of being solid, but you can see that it looks very particulate and very fragile. There's no way you could hammer that into a sheet. Aluminum and sodium, however, are very malleable. They're very ductile. You make aluminum wire, no problem. You can make sodium wire if you coat it in, like, oil so it doesn't detonate in the air. You can totally do that. Sodium metal is very soft. You can cut sodium metal with a knife, believe it or not. So you can shape it into whatever shape you want. And then going down the periodic table, the same thing happens. Metallic character increases as you go down. There's some more elements. You can see that as we go through them, they become more metal-like. And then you get to bismuth, which is just crazy looking. Yep, that's that section, and I think that's all we need to do today. So when we come back on Tuesday, what we're going to do is we're going to start here on molecular and ionic compounds. This is just a section to sort of segue into Unit 4 about what types of compounds we're going to be looking at, because we're going to talk about how to make ions. We're going to talk about how to make ionic compounds versus covalent compounds. We're going to talk about bonding, all in Chapter 4. And we're going to draw Lewis structures of everything. And that'll be how we round out the entire course, really, is just Lewis structures, Lewis structures, Lewis structures. So on Tuesday, we're going to finish Chapter 3, it looks like. Hooray, thank Thor. I'm so done with Chapter 3. You're so done with Chapter 3. Nobody wants Chapter 3 anymore. It's been here forever. Time to put it away. But we'll get to that tomorrow. I do want to thank everyone for coming out to the extra lecture. I realize that it is an extra time commitment for this week, and we all have enough to do. But if the sooner we get through all the material, the sooner we can prepare for exam number 2 and the final, which are coming up, because the end of the quarter is quite soon. No upcoming due dates. I am going to post a lab video at some point this week for lab number 4. Grading on lab number 3 is mostly done. I have about 40 more labs to do out of 90, so I'm getting there. Hopefully I'll have that posted Thursday or Friday. Please keep an eye out for a few upcoming announcements that I'll post later tonight regarding the deadline to drop the course. That's the end of week 8. And also course evaluations, which are worth a little bit of extra credit. Everybody loves extra credit, so watch out for those announcements, and we'll see you tomorrow. Take care.